Okay, so let's start. So it's a pleasure to welcome Clemens Berger from Nice, who will talk about moment categories and operads. So please go ahead, Clemens.
Thank you very much, Joachim, and I would like to thank all the organizers for giving me the opportunity to talk in this seminar. I want to give you some insight in a concept I'm working a long time already on, but I just finished somehow writing down the things very recently, and so I will give a small introduction of what I'm talking about. Then I will speak about moment categories. Afterwards, hypermoment categories, which is a slight generalization. Then the plus construction, and finally I will present two monadicity results. So what is a moment category about? It is actually, it starts from a certain factorization system on a small category. And I call this factorization system active inert factorization system because it has been introduced for the category of finite-based sets and mappings between them by Jacob Lurie in his work on higher algebraic structures and infinity operads. And I somehow generalize properties of this factorization system to other categories. And the idea is that such a factorization system induces a notion of moment, which actually is a funny term for a endomorphism of an object, which is split. So it's a split endomorphism. And so the presence of these moments gives rise to a moment category. And then there are also unit objects in the category, and altogether they give rise to an opera type. So to each category corresponds a certain type of operads. And then you can try to represent these operads in a different way. And one way to do so is by using a plus construction. And then you can represent the operads as a presheaf satisfying certain Siegel conditions. So this is more or less what I want to explain you in more detail. And I will explain it actually by examples. So I will, so I will more or less try to give a guided tour through 5 small categories which carry a moment structure. So the first one is Siegel's category gamma. Then it's the simplex category delta. So I hope that at least everyone is familiar with delta. Then there are higher dimensional generalizations of delta, which have been introduced by André Joyal and which are denoted theta n. Then there is the dendroidal category omega, introduced by Ike, Moerdijk, and Itai Weiss. And finally, there is the category, the graphoidal category, which is also denoted gamma. So I added an arrow as an index to distinguish it from Siegel's category gamma. And this category has been introduced by Hong Chu, Marcy Robertson, no, I'm sorry, by Marcy Robertson, Philip Hackney, and Donald Yeo. So I will try to convince you that all 5 categories have one thing in common. They are a moment category, so they carry a certain factorization system. And you can associate to such a factorization system a notion of operads. So for gamma, it's the classical notion of symmetric operad. For delta, it will be the notion of non-symmetric operad. For theta n, it will be the notion of globular n-operad, introduced by Michael Batanin. For omega, it will be some kind of operad indexed by trees. So I call it tree hyperoperad. It is, and for this graphoidal category of Marcy, Philip, and Donald, you get graph hyperoperads. Now, to each operad, you can also associate a notion of algebra, and especially the terminal algebra. And so especially algebras over the terminal operad. And these algebras over the terminal operad, I call them C-monoids. And so it's well known that the terminal symmetric operad has algebras commutative monoids. The terminal non-symmetric operad has as algebras associative monoids. The terminal n operad will have as algebras n monoids. But so these are monoids with n monoidal structures which distribute mutually. So for n bigger or equal to 2, these are just commutative monoids again. But what is interesting is that for omega, you get as monoids, so as algebras over the terminal tree hyperoperad, you get symmetric operads again. And for the terminal graph hyperoperad, the algebras are properads of Bruno Valette. So the notion of C-monoid is also an interesting notion. And what is interesting is in this context, you can homotopically weaken the notion of C-monoid, and then you get very well-studied objects as well. So in the case of gamma, you get E-infinity spaces. In the case of delta, you get A-infinity spaces. In the case of theta n, you get En spaces. And in the case of omega and the graphoidal gamma, you get respectively infinity operads and infinity properads. So I will not speak much about this homotopical weakening, but it just tells you that you have enough combinatorial structure to get a consistent homotopical notion of C-infinity monoid. So this way of encoding operatic structures by categories has been done in different ways, and actually I was very much inspired by the concepts which already exist. So I would say the first one to introduce a categorical notion which encodes operads was Clark Barwick, and he called it an operator category. And actually the difference between moment categories and those concepts which already exist is that they somehow only take the active part of the structure and they replace the inert part by another structure. So in Clark Barwick's notions, this is a pullback structure. Then there is the notion of operatic category of Michael Batanin and Martin Markle. where the inert part is replaced by an abstract fiber structure. Then is the notion of Feynman category of Ralph Kaufman and Benjamin Ward, where the active part, where the inert part is replaced by a symmetric monoidal structure. And finally, there is a notion of categorical pattern, where this time it is very, very close to a moment category. The only difference is that it works in an infinity categorical context, while I'm working just in an ordinary categorical context. But you have also you have also an active part and an inert part, and there are other similarities. So it is really a very similar concept, and this concept is due to Hongzhu and Rune Hauxing. So that's I won't have time to explain exactly how to pass from moment categories to these already existing concepts, but there is really a very close relationship. So what's a moment category? It is a category equipped with an active inert factorization system. So each map can be written in a essentially unique way as an active morphism followed by inert morphism. There are two axioms. So the first axiom is that each inert map has a unique active retraction. So it has a unique retraction which is active. And the second axiom is the following. So if you have a commuting square like on the left with parallel inert maps and active maps, so I actually denote inert maps always with like I and I prime here, and active maps always like F and J and J and G here. So with some middle so a vertical line. So if you have a commutative square like on the left, then each of the inert vertical maps have retractions, which I denote by R and R prime. And the square you get on the right must also commute. That's the second axiom. So it is a quite weak axiom, and in all cases I know it is automatically satisfied. So I use this axiom. So this is a moment category. So now what is important is the following thing, that if you have an inert map, then this has a retraction, and if you have a retraction and a section, you can also compose them in the other way around. First the retraction, then the section, and what you get is an endomorphism, and actually it's a split endomorphism. And such a split endomorphism, I call it a moment. And now it is very easy to check that inert subobjects of an object of a moment category are the same thing as these endomorphisms you get by composing the retraction with the inert map. And so these moments, you can just characterize them as endomorphisms, such that if you factorize it into an active followed by the inert, then if you compose it in the other way around, you get the identity of A. So if you have an active inert factorization system, you can specify certain endomorphisms by this property, and I call them moments. Then you can define the set of all moments of an object. And what is now very important is that the factorization system allows you to transport these moments along morphisms. So how you do it? If you have a map F from A to B, and you have a moment on A, so an inert subobject, which I call A phi, with a retraction, then you can define a moment on B. How you do it? You have the composite of the inert map phi with F, and you decompose it as an active map F prime followed by an inert map psi inert. And then, because this inert map has an active retraction, this gives you a moment on B. So you just define the push forward of the moment on A by this commutative diagram, which is written there. And this is very important. So this is some kind of image factorization, if you want, but a very abstract one. So you can push forward moments along any map of your category. Now, I just want to give you one property which is not at all needed in all my talk, but which is a very funny property. If you look at all moments of an object, then normally it's just a set. So it is just a set, but it turns out that you can compose these endomorphisms and you get automatically another moment. So the set of moments of an object is a submonoid of the endomorphism monoid of an object. And now in general, these moments do not commute, but they have some kind of skew commutativity, which is expressed by this relation phi psi phi equals phi psi. This relation is true for any two moments of the same object. And funnily enough, this relation exists in literature, in semigroup literature, and a monoid of idempotent elements which satisfies this relation is called the left regular band. So those who are acquainted with semigroup theory, they know this concept. It is a very important concept in semigroup theory. And it is somehow automatically given in this context, and you can consider moment categories as categorification of left regular bands. So left regular bands are moment categories with one object. Now, what are the examples? The examples, so the first one, the most important one, is Siegel's category gamma. So unfortunately in literature, most people do not use the initial definition of Siegel, but they use the fact that the opposite category of gamma is the category of finite sets and partial maps. And also it's the same thing as saying finite based sets and based maps. So an external base point can be used to define partial maps. But for me, it's very important not to dualize, but to take the initial definition of Siegel in order to have the right direction of the arrows. So an arrow from a set with m elements to a set with n elements is given by a partition. So is given by subsets of the target, which are mutually disjoint and indexed by the elements of the source. So now, if the subsets cover the target, I call this morphism active. So such a morphism is active if the union of the disjoint, mutually disjoint subsets cover all the target. It is possible that parts are empty, so you can have empty parts, but you have a partition of the target into disjoint mutual disjoint subsets. But you can also have such disjoint subsets which do not cover all the target. And in particular, you can have singleton subsets. And if you have such a map with singleton subsets of n, then this corresponds just to an inclusion. And this corresponds to inert maps. So inert maps are inclusions, but they are somehow represented by singleton subsets of the target indexed by the elements of the source. And you can just check that this gives you a factorization system. So every map in Siegel's category gamma factors as a partition of the target followed by an inclusion. So the active maps are partitions and the inert maps are embeddings. The simplex category is the category of finite ordinals. And here you have a similar factorization system. So an order preserving map is active if it is endpoint preserving. This means that it takes 0 to 0 and it takes m to n. And it is inert if it is distance preserving. This means that it respects, it satisfies this relation f of I plus 1 is f of I plus 1 for all I. So you can also say that it is an inert map represents an inclusion of a subinterval. So f identifies m with a subinterval of n. And again, it is easy to check that this is a factorization system, and it is not the usual one. It is not epimono. It is really a different one. But it is very closely related to this factorization system of Siegel's category gamma. Now, if you have a moment category, you have different concepts. You have the concept of a centric moment, which means that the inert part of the endomorphism is the only inert section of the active part. So in the definition, we know that if each inert map has a unique active retraction, and one says that the moment is centric if the converse is true to some extent, that if you have an active map, then it has only one inert section. And this, so one can show that if you have two centric moments of the same object, then they commute. So if all moments of a moment category are centric, then they all commute, and actually this is even an equivalence. Then one can define what is a unit. This is a very important definition. So, but of course I cannot somehow explain all the aspects of this notion. But so formally a unit is defined by the property that the identity of the object is the only centric moment. But you also, for some reasons, you also require that there is at least one non-centric moment. So the set of moments is not reduced to just the identity of the object. And so this is some kind of primitivity notion. Now, the more important aspect of the notion of unit is that whenever you have an active map whose target is a unit, it must admit exactly one inert section. So, so every active map whose target is a unit admits an inert section, and actually a unique inert section. Now, a moment is called elementary if its canonical splitting is over a unit. So somehow the elementary moments are the smallest moments, which nevertheless are centric. So one has to be a little bit careful about this notion of elementary, but you will see in the examples what it means. It's a very intuitive notion. And the set of elementary moments is a subset of the set of all moments, which I will denote by L sub A. And it can very well be that an object has no elementary moments at all. Then I call it a nil object. So the number of elementary moments is a notion of cardinality of this object. Now, what happens in our examples? So in gamma, the empty set is the only nil object, and the singleton is the unit. And so elementary inert subobjects are just inclusions of singletons, so they are just elements of your object. And so the cardinality of elementary moments of an object is just the cardinality of this object in the usual sense. In delta, it's very similar. So the only nil object is the singleton ordinal, so the ordinal which actually is just a point. And the unit of delta is the segment 0, 1. So elementary inert subobjects of an ordinal are just the segments of these ordinals. And you know that n is an interval of length n, so it has n segments, so the cardinality of the ordinal n is also n. Now, what is a C operad for a unital moment category C? I will explain in a second what the term unital means. So it means that you have enough units to some extent. So what is how you define abstractly the operad associated to a moment category? So you have to decide in which category your operad takes values. So you can take sets if you want, but you can take any symmetric monoidal category. And a C operad assigns to an object of your category C an object OA of your category E, together with a unit map for each unit of your moment category, and a composition map which takes the following form. You have O of A tensor OF into OB for each active map. So an operad composition only needs the active subcategory of your moment category, and you actually associate to an active map the following tensor product, and you take the tensor product over all elementary moments of the source of A, and you push forward this moment along F. Now, if you push forward an elementary moment, you get a moment of B, but it is not anymore elementary. And so you have a splitting. So remember that the splitting of a moment, I called it by B sub the moment. And your operad takes a value on this object. So this OF is a tensor product of these values. And then this composition must satisfy certain unit constraints, associativity constraints, and equivariance constraints. So let us just have a look for our examples what it does. So a gamma operad, so it's indexed by the objects of gamma, so by the natural numbers. And for an active map from M to N, you have a map from OM tensor OF into ON. But an active map, we have seen, is just a partition of the target. And this partition is N1 until to Nm, and you have evaluate your operad at these subsets of N. And then you have an arrow into the value at the target. So this is precisely the data of an operad. And so the constraints are the usual ones. So this is for gamma. Now, if you take delta, you have actually the exactly same data, but you see the notion of partition has changed. Here you have an ordered partition of the target. And therefore, the operad notion you get here is the notion of a non-symmetric operad. You have no symmetries, and you have and your partition, which is given here, is an ordered partition, while a partition in gamma is an unordered partition. Now, just for unital moment categories, you have to require that a set of elementary moments is finite. Otherwise, the tensor products are not defined. And you also should require that each morphism gets a unit active map from a unit. So in our case, it's gamma and delta. We have just a single unit, and you can check that there is a unique map from this unit to each object of your category. Siegel's category gamma is very important because it plays a universal role. For every unital moment category, you have an essentially unique functor from your moment category to gamma. This is and actually the functor is easily defined. It just associates to an object of C the set of elementary moments viewed as an object of gamma. So this functor is cardinality functor. And you can just check that actually it commutes with the active inert factorization system. And this means that active maps in C can always be considered as some kind of generalized partitions. And inert maps in C are generalized embeddings. Now, if you have unital moment categories, you can define a Riesz product. And the Riesz product is a asymmetric structure. So somehow you use the moments, so you have two moment categories, and the objects of the Riesz product are pairs given by an object of the first moment category, and then a family of objects of the second moment category. And this family is indexed by the elementary moments of A. So you have an object A, and then you have a family of objects B alpha, where alpha runs through the elementary moments of A. And the morphisms are given by a morphism in the category A from A to A prime, and a bunch of morphisms in the category B from B alpha to B prime beta, where you have a morphism each time the moment beta is a submoment of the push forward of alpha along F. And so why is this important, this Riesz product? This is important because Joyer's categories theta n are iterated Riesz products of delta. And so this Riesz product construction gives you moment structures automatically. And so this gives you an active inert factorization system on theta n. And the associated operads are precisely Michael Batanin's n operads, which are trivial below. So this is what is called n-1 terminal in his terminology. So let me just give you a small insight into the moment structure of theta n. So the objects of theta n correspond to n-level trees. So trees with n levels of height n. There is a single unit, which is the linear tree of height n. And this canonical cardinality functor sends an n-level tree to the set of height n vertices. Now, in order to understand the operads, the Cn operads, you have to understand the active maps. And actually, these active maps, they are already contained, not in explained exactly in this way, but they are contained in Michael's original paper on globular n operads, and they correspond to tree decompositions. So partitions of the tree T indexed by S. But now you have to define what it means, a tree partition. And this is done by associating to each tree actually an n-graph, an n-globular set. And it is this n-graph structure which gives you the way how to decompose. And I just give you the recipe. So first of all, this gives you a little bit. So I just take delta Riesz delta, so theta 2. So you have a 2 ordinal, 2. You have an ordinal 2, and then so this 2 is drawn below. You have 2 edges here, and then the cardinality is 2. So you have to give 2 other ordinals, which you put above the vertices. So I take as first ordinal 2 here. So I have to put 2 edges above it, and 0 here. So I have to put nothing here. And so you see, you get a 2-level tree. And now the graphical structure is defined as follows. Somehow this is given by the inert morphisms. So you have 3 inert morphisms from U0, the unit of height 0, into this tree. And this corresponds to 3 sectors here. Then you have 4 inert maps from U1 into this tree. They are given by T4, T5, T6, and T7. So here you have 3 sectors. And here you have just 1 sector because there is no edge here. And then you have 2 inert maps from U2 into this tree, which are given by these 2 sectors here. And the globular structure is given by the planar structure of this tree. So this 2 cell has as source T4 and as target T5. This 2 cell has as source T5 and as target T6. And these 2 cells have same source and target, namely TOR1 and TOR2. And this 1 cell has these 2 as source and target. So if you now picture it, this 2 graph, you get this on the right, which is called a 2 globular pasting diagram. And you see you have 3 0 cells, TO1, TO1, TO2, TO3. You have these 4 1 cells, and you have 2 2 cells. And so the inert structure of θ2 contains all the globular pasting diagrams of this. And it tells you how to decompose a tree into subtrees indexed by another tree. So that's just to give you some kind of feeling what is this active inert factorization system of θn, and why θn operads are precisely Michael's n operads. So now I will go very, very quickly to this. So as I said, C-monoids are algebras over the terminal C operad. So to simplify the situation, I just assume that I have a single unit U which has no symmetries. Then you can define endomorphism operads in the usual fashion, where the cardinality of an object just tells you how many tensor factors you have to take. O algebra structure on X is just given by a map of C operads from O into the endomorphism operad. And the C monoid is an algebra over the unit C operad. So if in your category E, the monoidal structure is the Cartesian product, then the unit C operad is the terminal C operad. And now what is important is that you have a pre-sheaf presentation for the C monoids. C monoids are precisely pre-sheaves on the active part, which satisfy that on an object you have this decomposition into tensor products, and on a morphism, on an active morphism, you have also a decomposition into many-to-one operations, so to speak. And it is again induced by push forward of moments. So this is for general symmetric monoidal categories E. If your symmetric monoidal category E is Cartesian closed, you can get a step further. You can actually define pre-sheaves on the whole category C. And the conditions you have are stronger. So you have to impose that for every nil object, you have the terminal object as value. And then you have the Siegel conditions. So for every elementary moment, you have an inclusion of the unit into your object. And these inert maps define contravariantly a projection map from X to A into this product of X to U. And the strict Siegel condition just means that this must be an isomorphism. And you can show that, in the Cartesian closed case, these two conditions are almost equivalent to what is written here. So what is important is that you can use this definition of C monoid to define C infinity monoids. And that's actually what people do in literature. So now I will come to hypermoment categories. So hypermoment categories are a slight generalization of moment categories. What you retain is just this cardinality functor. But you drop the condition that each inert map has an active retraction. So you retain the active inert factorization system, the cardinality functor, but you drop the condition that each inert map has a unique active retraction. The cardinality functor must preserve the factorization system, and there must be a lifting property which which is means the following, that if you have an element in the image of your cardinality functor, then this element can be lifted into an inert map from a unit into A, and in a unique way. And actually this unit must satisfy this this second axiom of a unit. So this is very important. So this is a hypermoment category, and there are important hypermoment categories which are not moment categories. So the dendroidal category of Ike and Itai is such a hypermoment category. So the objects are dendrices. And now I will describe the morphisms using already the active inert factorization system. And actually I use also the epi-monofactorization system. So you have two factorization systems, and they combine into a triple factorization system. So every map factors into epi, which is a degeneracy, followed by an active monomorphism, followed by an inert monomorphism. So the epis are also active if you want. And so you have a triple factorization system, and this triple factorization system is precisely this factorization system into a degeneracy, followed by an active mono, followed by an inert mono. And usually the active monomorphisms are called interface maps, and the inert monomorphisms are called autophase maps. And the geometric meaning of an interface map and the autophase map is completely different. So an interface map is an insertion of a tree into a vertex of another tree. So it is dual to a contraction of edges. So in order to be able to insert a tree into another tree, you must ensure that the leaves of your tree you want to insert correspond to the incoming edges into the vertex where you insert it. So this is called an insertion, and this corresponds to a partition actually. What you do is that you partition your target where one part is given by your inserted tree. And then you, so this is a partition, while the inert monos correspond to embeddings. So an embedding means that you can see a tree as a subtree of another one. So this is a dendrix embedding. And the cardinality functor takes a dendrix to the set of its vertices, and the units are thus just the dendrices with a single vertex. And these dendrices with a single vertex are called corollas. And you have a corolla for each natural number depending on the number of incoming edges. So there is there is some kind of directed version of this dendroidal category, which has been introduced not so I think about 5 years ago by Philip Hackney, Marcy Robertson, and Donald Yore. And the objects are directed graphs where you have also directed leaves. This means that you have edges where only on one side there is a vertex, on the other side it's open, but you direct them. And the only condition you impose is that there are no cycles. There are no directed cycles. And again, there is a triple factorization system, degeneracy, active mono, inert mono. And again, the active monomorphisms usually are called interface maps, and they correspond to inserting a graphics into another graphic, into the vertex of another graphics. And because the leaves are all oriented, you have a similar constraint to being able to insert the graphics into the vertex of another graphics. So these are the interface maps, and the outer face maps are embeddings of graphices into graphices. So you consider a graphics as a subgraphics of another one. And so the cardinality functor again takes the graphics to its vertex set. The units are graphices with a single vertex, and if you have only a single vertex, then you have to tell me how many incoming edges there are and how many outgoing edges there are. So you have corollas which are indexed by two natural numbers, n and m. Actually, the nil object, there is a single nil object in omega and also in the graphoidal category, which is just the free living edge. The free living edge is the only nil object. And now you have embeddings of hypermoment categories, so which means that these embeddings are compatible with the cardinality functors. The simplex category embeds into the dendroidal category by viewing an ordinal as a linear tree of the corresponding height. And a dendrix, so a tree, can be considered as a graphics just by orienting all edges towards the root. So if you orient all edges towards the root, you get a graphics. So this gives you the embedding of omega into the graphoidal category. And now, as I already said, the corresponding notion of operad are these tree and graph hyperoperads. So this is an idea which goes back to Getzler and Kapranov. But what is more interesting for us are the monoids. And the monoids are known objects. So omega monoids are symmetric, single-colored symmetric operads. And these gamma monoids are precisely the single-colored properads of Bruno-Wallet. So you have seen, I must a little bit hurry up, so I will. You have seen that symmetric operads appear twice. They appear as gamma operads, so operads over the moment category gamma, but also as monoids for the dendroidal category omega. And this is not somehow a coincidence. There is indeed a close relationship between gamma and omega, which somehow is related to different models which exist in literature for infinity operads. So Lurie's model is rather shaped on gamma, while Ike, Moerdijk, and Donischal-Cieszynski's models are rather shaped on omega. And these two ways of defining infinity operads is precisely the relationship between gamma operads and omega monoids. And it's interesting that this kind of relationship has been worked out to some extent in the context of colored operads by John Baez and James Dolan. And they call it the plus construction. And so there is a plus construction also for moment categories. And so I will present you this plus construction. And so the upshot is that if you apply the plus construction to gamma, you get a category which is closely related to omega. So, and it is actually very interesting that in the setting of moment categories, the plus construction is very easy. It is just you take the simplicial nerve of your moment category, and then in this simplicial nerve, you take certain simplices only, namely those simplices where all arrows are active and where you begin with a unit of your category. So this is what I call a C tree. So you have a unital hypermoment category C. So a C tree is just given by a chain of active morphisms of length m. And the only condition is that all arrows are active and the first object is a unit of C. So a morphism is given by a map in delta, and the natural transformation of from A to B phi to the composite. So this allows you to compose these arrows actually. And the only thing you assume is that any so that it is pointwise inert. So the induced maps here are all inert. And the plus construction is just the category of C trees and C tree morphisms. And a vertex, each tree has vertices, so these are very abstract trees. But a vertex is given by an inert map from an arrow into your simplex. So there is some kind of joyal duality which is hidden here, because you see that vertex is normally it's something of dimension 0, and here it seems to be of dimension 1. So there is a joyal duality which is hidden there. And the theorem, so which is really inspired by Bayes-Dolan, is that, so first of all, C plus is a unital hypermoment category. And even if you start with a moment category, C plus will not anymore be a moment category, but it's just a hypermoment category. And you get the identification of C operads with C plus monoids. So this means that you can represent operads by presheaves. That's the gain in this plus construction. So I think this will be my last slide. I will just give you some impression how it works in practice, this plus construction. And so I will represent dendrices, so objects of omega, as gamma trees, so chains of active morphisms in gamma. So here is a dendrix. You see you have 3 vertices and you have 3 leaves, you have 1 root. And I represent this by this chain, which is on the right. And actually the recipe is very easy. It's so you should actually, on the right, this chain, you should put it a little bit down. So the 1 corresponds to the 1 root, the 2 corresponds to these 2 edges, and then the 3 corresponds to the 3 edges of level 3. And the active map is just given by the things which are supported. So the first map is that the root edge supports 2 edges, and the second active map is that 1 supports 1, 2, and 2 supports 3. So you have a partition of your target. Of course, if you want, you can also dualize, and then you look at from top to bottom, and you have just surjections. So these active maps are actually active monomorphisms, because all parts are non-empty, and therefore by dualization they correspond to surjections. So you have a two chain of surjections, which gives you this tree. But you see, this tree is very special. It is what is called an open tree, because there are no stumps, and it is pruned. So you go until to the top with all leaves are on top level. So this here shows you that the gamma plus construction, if you restrict to monomorphic active maps, gives you precisely the subcategory of open pruned dendrices. But now, in the definition, you don't require that your active maps are monic. They can be any active maps, so this means that parts can be empty. And if a part is empty, then you just stop there. So for instance, on the picture above, if instead of 3, I would take the empty set and I would replace the target 3 by 2, then I would have to drop the edge labeled by 3, and this gives rise to a stump, a vertex with no incoming edge. And so extension of this gamma monic to all gamma plus defines you actually a full subcategory of omega of reduced trees. And there is work of Chu, Hauxeng, and Heutz which shows that this subcategory is enough to from a homotopical point of view. And it is also enough from an algebraic point of view, because gamma plus monoids are also symmetric operads. So this somehow gives you or shows you how to relate, how to represent symmetric operads in two ways, either as operads for gamma or as monoids for gamma plus or of omega. So I will stop here. Thank you for your attention.
Okay, thank you very much, Clemens. Are there questions or comments?
How do you compare this with the other approach of operatic categories or Feynman categories? Or
it is, I think, a very structured way of encoding operads. And so, as I said, if you want to have an operatic category, actually, it is very easy. You take just the active part of a category, and you take the dual of it. And because of your cardinality functor, you have a map to dual of the active part of gamma, and this is just finite sets. So you get an operatic category in the sense of Michael and Martin, where the fiber structure is given by these push-forward operations I have mentioned in the very beginning of my talk. And so the operator categories of Clark-Barwick are just a special case of it, where the fiber structure is given by pullback. And the Feynman category of Ralph and Benjamin, they arise also quite easily. I have defined these C trees, abstract C trees. And if you add a single condition to your hypermoment category, which I call extensionality, then you can define an abstract insertion of C-trees into vertices of C-trees. And this defines your Feynman category. So I can very easily define the corresponding objects in these other settings, but there is, in general, not a way back to lose structure. If you throw away the inert part, you lose really some structure. So hyperstructure or the symmetric monoidal structure is not enough to recover the inert part. So one of my aims is really just also to emphasize the importance of the inert structure in this. Even though one can get rid of it, but when one gets rid of it, one loses something.
Which brings me to my question. So you said that for any moment category, you could speak about operads over it, but using only active maps. But then is there a notion of co-operad over a moment category which would maybe use inert maps?
I don't know. I did not think about it.
Moi, je ferais plutôt un truc opposé, avec la catégorie opposée. And do you recover, this provides you with a very general framework for this type of operads. But then when you have a certain type of opera, I mean, there are universal constructions, convolution algebras, causal duality, etc. Did you already study this within your framework?
Not me, no.
Okay, good.
but I know that there must be some relationship. So this is things to do. So one, for instance, which I very much like to understand better is the relationship between the plus construction and the W construction. And there is certainly a relationship, and then there is a relationship between W construction co-Barbar, as you know. So there is not a big step to causal duality. So I think that all this is related, but I also believe that Martin Markel and Michael Batanin, they have already done a lot of work on causal duality in their framework of operatic categories. Somehow it would be interesting to know whether this more complete structure of a moment category can give perhaps some simplification of causal duality. This would be nice. So.
I'm sorry, I have a last question after that. I should do I understand correctly that your inner part gives you the monoidal structure inside which, I mean, for which you have all the notions of symmetric operad, non-symmetric operad, properad, etc. Did I understand correctly?
Yes and no.
I'm a student.
No, you see, perhaps I will go back because this is a very subtle point and it's a good question. You see, C monoids, for instance, they apparently use only the active part. Because it's a presheaf on the active part. But if you decompose a map F into its elementary constituents, you use implicitly the push forward of moments. So you use the inert part. And you cannot do without. And at each level you have this phenomenon. Even though perhaps the object of a presheaf is only defined on active morphisms, in order to have to be able to define these two constraints, you also need the inert part. The inert part is hidden in this push forward of the moment. And that's really, so if you throw away the inert part, you have to add something. You cannot just do with the inner part.
So I asked you that question for the following thing. I would say the other general frameworks allows us one to encode cyclic operads or modular operads, but I don't know any monoidal structure for which these types of operads are monoids. So can you, and you know, causal duality theory for operads, non-symmetric operads, properads work because they are monoids in the monoidal category. So is it, I mean, do your framework encode cyclic or modular operads, for instance?
I don't think so. So only, so it's exactly for, like for operatic categories, you have to cheat.
Shell is here, be careful.
You can represent them as monoids for a certain category, but not as operads for a genuine moment category. And I think so, but it is also a nice framework, you see, because it's also a nice framework, but to be honest, there is no moment category such that operads for this moment category are modular operads. But there is a hypermoment category which has also been developed by Marcy Robertson and Philip Hackney, whose monoids are modular operads. So you can represent modular operads as presheaves, but somehow, yeah, it's a little bit cheating.
So I actually have a related question. So if I consider concyclic category, does this have a generalized moment structure? And is this related to cyclic operads?
So this is a very good question. Of course I tried to do it, but there are some problems with moment structures. So there is no moment structure, but perhaps there is a hypermoment structure. So I must say that so it's a very good question. I cannot definitely say no, but so I tried it with a moment structure, and there it is no. But I did not try it with hypermoment structure. The problem is, the problem is related to the nil objects actually. So yes, so there are some obstructions to do so.
Okay, there are also a couple of questions in the chat. Javier, do you want to ask your question yourself?
Yeah, sure. Hi, Clemens.
Hi.
My question is if there is a general procedure to build some kind of model structure, some presheaves or maybe simplistic presheaves over these hyper or moment categories. I mean, just based on the combinatorics of these categories.
Yes, that's. I'm sure it is, but it's not yet done. So that's one of my projects. So I think that you can somehow give a common framework for the model structure of Reschke on weak end categories and the model structure of Denichal and Ike for the dendroidal Siegel spaces. So this is, I'm sure that it is possible.
Okay, that's very nice. Yeah, thank you.
And then there's a question from Michael Batani. Misha, are you there?
Yeah, I am here, but I have bad connection. So if I switch it on, it's usually everything freezes. I'm trying to use chat. It works better.
But we can hear you very good.
Okay. Yeah, so I just want to know if you can describe braided operads as an instance of operads over a moment category. So is there any moment category for braided operads?
I don't know. It's a good question.
So I can imagine that it's some kind of think which you can construct out of configuration space on the plane, and you probably can mimic gamma, but it's a bit.
Yes, yes.
The technical details will be very interesting to see.
Yes, yes, that's a good question. It's possible.
Okay.
Are there more questions?
Yes, I have a question.
Yes.
Clemens, I just wanted to get the intuition, maybe just to check if my intuition is correct. So the objects of the moment category are basically what the input shapes of multimorphisms for the corresponding C operad should look like, right?
Right, yes.
Yeah, so do you have a nice way of calculating a wide subcategory of the moment category such that C operads are nicely monadic over presheets on this wide subcategory? Like in the case of gamma and delta, you would probably get the finite sets and bijections for gamma and just the set n for delta.
So I have something which goes in this direction. Where I had prepared much more. So what I can define is, so it goes a little bit in your direction, but it's not precisely what you are saying. In all examples I have discussed, I can define what is called a Siegel core. Siegel core. It's just a subcategory which is spanned by the deal objects and the units. And this is very small. You see, for delta, you have just this. For theta n, you have actually a globular n cell. For omega, you have the edge inclusions into corollas. And for the graphoidal category, you have edge inclusions into directed corollas. Then you can look at pre-sheaves on it. So this is some kind of a graphical notion. So for delta, you get honest graphs. For theta n, you get n graphs. For omega, you get a notion of multigraph with several inputs and one output. And for graphoidal category, you get a directed multigraph.
Yeah.
And then you can define actually a monad on these graphical categories. And the free objects on, and you can recover actually the hypermoment categories as Kleisli categories of a certain monad on these shapes.
Yeah. Yeah. Okay. So it does.
That's more or less. This goes in your direction.
It does sort of partly fit into this picture. Yeah. Yeah.
But Clemens, here the core only contains a inert map, right?
Contains? Yes. It's a subcategory of the inert category. Exactly.
And it has less objects also because it contains only the ones which are generating in some sense for the tree. Okay.
Any other questions? It was good we got the question to let Clemens get to the end of his slides. If there are no more questions, then maybe we just thank Clemens again. And thanks for the very nice talk.
Thank you.